So for today, I'm going to shorten things up a little bit for today. We're not going to do this stuff for today. We're just going to, so this will be pretty light today. I'll hit the factoring by grouping tomorrow. So let's review just GCF stuff. Okay, now GCF, greatest common factor, give me 1 to 5 on your familiarity with greatest common factor. Okay, I'm seeing lots of pretty high numbers, right? Okay, that's good. Let's review how we find, do you know how to find a greatest common factor if you have big numbers? Anybody know? Like, what if I had a list of 3 big numbers and you're supposed to find the greatest common factor? This is just for your notes. You wouldn't have to read through all this stuff. It's in the book. Make sure we're getting to a point now, I think I mentioned this yesterday, where things definitely become more sophisticated. Now is the point where you definitely need to at least skim the book as we're going through this, right? So what chapter are we in the book right now? What's the last? 6. That's right. Everybody knows how to get to the book, right? Okay. This is section 6.5 we're in. So it take literally 5 minutes or less and just skim through the book. Look, you don't have to read it text, word for word. That's not how you read a textbook. You read for information, right? So look for the stuff in boxes, look for the bold stuff, look at an example or two if you need to, right? Maybe you don't need to look at examples after today, but take 5 minutes and just review that stuff. It does a couple important things. It gives you some information in a slightly different way. But the other thing it does is it provides additional stimulus to your brain, to those pathways that you're starting to grow, so you understand this stuff, right? Literally, your brain has to grow these axonic and dendritic pathways that interconnect your brain, and that's what learning is creating and then leveraging these pathways. To help your brain do that, you don't want to study all in one session. That doesn't work. It's better to study in multiple small sessions. So you're hitting your brain again and again with repeated stimulus. It's like training in athletics. You can't just go in and lift weights for 12 hours and get stronger, right? You got to break that down into 6 2-hour sessions, spread out, and then you get stronger, right? Your body just can't immediately adapt to too much stimulus. You have to spread it out and give it repeated stimulus. So don't, just kind of every now and then, if you could hit it, like even in class is going to be one opportunity. If you could just look at your textbook briefly and do some homework, there's another opportunity for your brain to think about this stuff, okay? But try to get a little bit extra math in every day going forward, because you're going to probably need to. Things just get a little tougher. So what about this? I've mentioned this. How do we find the GCF of a bunch of big numbers? What is the GCF? Okay, but what's that mean in your own words? Don't look up here. Just everybody, like, if you had to describe that to your younger, the biggest. Okay, good. The biggest number that goes into all the numbers, even, right? Okay. So how do we find that? Well, when you get big numbers like this, that's kind of a tough thing to do by just trial and error, right? Does anybody know what we could do here to find the GCF? Okay, well, factor tree might be a good idea, right? How about a factor tree? So let's make a factor tree and then see if you guys can tell me what to do with that factor tree. So what's a factor tree for 144? And when we're making a factor tree, you guys know how to do this stuff, but I'm going to help you get a little better at it. When I'm making the factor tree, the numbers that I create, I could just do, 2 and 72, and that's fine. But there's maybe a better way to do it. If I do 2 and 72, then one branch is done and my other branches grow really long. I'd rather kind of spread it out more uniformly than have a really long tree. You see what I'm saying? So what might be a better way to break that up?
18 and 8.
Okay, I heard a bunch, and they're all pretty good. How about 12 and 12, right? It's a perfect square. That's going to be a good idea for us to always start with a perfect square if we can, because later on, I promise you, that's going to be a much bigger deal. Later on, when we're using some other factoring methods, we're going to specifically be looking for perfect squares. So when you're using a factor tree, always see if you can find a perfect square as early as possible. Well, we found one, 12 and 12, and now I'm just going to do the same thing in both branches. How would 12 break down? Probably 3 and 4. And 4 breaks down into 2 and 2. Now, when do I stop? Okay, when I get to prime factors, right? I get to numbers. The numbers, Yeah, when I get to, the numbers don't have to be prime. Like 6 is not a prime number. Well, actually, I don't say that. Yeah, they do. You're right. Never mind. For now, they do. Yeah, when I get to prime factors. Okay, factors that can't be broken up anymore. I'll do the same thing over here. So I know what 12 did. So couldn't I cheat a little bit and just say, well, 12 is going to break up into 3, 2, and 2. Good. Okay, what about 108?
12 and 9.
12 and 9. There we go. That's a good one. So we'll go 9 and 12. 9 breaks up into 3 and 3. We've already done 12 over here. 12 broke up into 3, 2, 2, right? 210, that's a pretty easy one. It's got a 0. 21 and 10, there you go. 10, 21, 10 breaks up into, okay. And 21 breaks up into, there you go, okay. Good? Make sense? So now what? Okay, the fact that this was the factor tree for 144, how could I rewrite that in a maybe a little more convenient way? Well, let's take one step first, is let's write the factors in increasing order. So I'm going to rewrite this as 2 times 2 times 2 times 2. There's all my 2's, agreed? Times what else? 3 times 3. Good. How about this guy then? Let's see. This one gave us 2 times 2. We got 2 of those times a string of 3 3's. Okay. How about over here? This gave us 2 times 3 times 5 times 7. Can anybody tell me what the greatest common factor is?
6.
Yeah, how come?
2 and 3
Okay, because the only common factors there were a single 2. Let's underline. We had a single 2 and a single 3, and that's it. There was no additional overlap. Everybody get that? Okay, give me thumbs on that. Does that make sense? Okay, so we see the GCF equals 6. Okay, what if we had, is there a more convenient way to write these factored forms of those big numbers? Because that, like, if these weren't tremendously big numbers, but if these were numbers in the trillions, that might be a pretty long list of prime factors. How could I abbreviate that a little bit? Okay, yeah, 2 times 2 times 2 times 2 is the same thing as 2 to the 4th times 3 squared. Over here we got 2 squared times 3 cubed. And over here we got just that, right? There are no powers, right? That's just 2 times 3 times 5 times 7. So let's write that, I guess. 2 times 3 times 5 times 7. So when we're trying to find the GCF, let's look at using this row where we've got these big numbers written in prime factored form using exponents, which is way better. How could we use the stuff in the blue box to find the GCF? What's the first step, probably? What do you think? I probably need to find, first of all, what are the like bases, right? I've got powers of prime factors, but which bases appear in all of those? Looks like I've only got 2's and 3's, right? So I'm going to have, I know I've got the bases 2 and 3, but I need to know what powers am I able to use? Well, what would it be? Let's see. If I've got a 2 to the 4th and a 2 squared and a 2 to the 1, what's going to be the power of 2 that's going to contribute to the GCF?
2 to the 1.
2 to the 1. If I have like bases, the GCF is only going to include the least power of the like bases. Agreed? Here's a way to think about that. How come? Because I could divide away, each of these would allow me to divide away a 2 to the 1, but this guy right here would not allow me to divide out anything bigger than a 2 to the 1. It's only got a 2 to the 1 to give. Make sense? So I get a 2 to the 1. And how about the 3's? Well, I've got a 3 squared, a 3 cubed, and a 3 to the 1. So again, the biggest power of 3 that I can undistribute is a 3 to the 1. Okay? You guys ever done anything like that? Maybe not quite that much, but pieces of that probably, right? Okay, now that's, numbers, no big deal, right? I wanted to do a big example with numbers, though, to get us ready to deal with polynomials, because now we're going to be dealing with terms that have not just numbers, but also variables. Does that make it harder? No, not at all. Okay, before we launch into that, though, let's just remind ourselves we're entering a section where we're really if you look in the book, I don't know what this one's called, but this is the section of chapter 6 where we're learning about, or we're reviewing and adding to our knowledge of factoring, right? Factoring polynomials. What does it mean to factor? Factoring is the opposite of multiplying. One undoes the other, right? When we multiply stuff out, you're very good at that. That's easy to do. We've had some practice with that with polynomials. In this case, it would just mean distributing that monomial, right? If we had multiple polynomials being multiplied together, we can distribute and add like terms, or sometimes we can use patterns, and we've practiced all that stuff. Now we're going to start going in the other direction. When we're factoring, our job is not to start with individual factors and multiply them all out and collect like terms. It's to do the opposite. We're starting with a bunch of separate terms, and we want to see if there's a way that we can break that up into a product of factors, right? In the same way that you guys would tell me that, let's see, how about 30 in factored form is what? What is that? I could just kind of do a factor tree in your head. What would that break up into?
3, 2, 5, 2, and 3.
Okay, there you go. Right, like a 6 and a 5, and the 6 breaks up into a 2 and a 3 and a 5. That was a little tough. I mean, not that hard, but factoring is harder for us to do in our brains, right? It's a process that we're not as familiar with. If I asked you to start with 2 times 3 times 5 and tell me the answer, you all could have told me that in about half a second, right? That's 30. Multiplying is easy. Factoring is a little tougher. To break something up into a product of factors is just not as normal for us, right? Okay, so that's the process. We're done with the multiplying or distributing or expanding. It's all the same thing. And now we're going to reverse the process and work on factoring. So finding the greatest common factor now from a list of monomials, not just numbers like we did a second ago, but now we've got actually monomials that have variables in them too. Well, we can be smart about this. We can break this into little pieces. First of all, we can deal with the number. Find the GCF of all the coefficients of the monomials. Okay, that's not going to be hard at all. Find the GCF of the variable factors. Okay, that one is actually easier, but we're just not as used to it maybe. And then we'll just multiply both of those together to get the total GCF of the entire polynomial. Let's look at an example. Like, how about this guy? This one has no coefficients, so that part's taken off the table. But what about the variables? Well, we just talked about this. If we write out x cubed, it's just a string of 3 x's multiplied together. If I write out x to the 7th, it's a string of 7 x's multiplied together. So the GCF would just be the common factors, which would be 3 of those from each string, right? So it's going to be an x cubed. But you guys could have told me that without having that middle step there, because we would I have the same base, which is x, and we can only factor out the smallest power of that like base, which is 3. Okay? Give me thumbs. How we doing? So what about this guy then?
2x cubed.
Okay, good, because the GCF, the number part of the GCF, the greatest common factor of 6 and 4 is 2. 2 is the biggest number that divides into both evenly. And the biggest common power of x is x cubed. Okay. All right, so what if I have a list of 3 of these things? Okay. Let's just skip all the, you guys see if you can just tell me the answer first. What is going to be the GCF? What power of A can I undistribute? Okay, good. I can distribute an A squared times a B squared. And if you want to see kind of the reason why, well, there it is, right? But we don't need that stuff. We can think of this in terms of exponents, which is way quicker and more compact. Okay, so again, this is probably overkill for you guys, but what is my GCF going to be? 3x. Okay. So now, here's the next part. If I know what the GCF is, if I want to factor the polynomial, what does factoring 3x out mean in less complicated words? How would you describe that to your younger brother or sister who's not at this level of math? What are you doing?
Take out the 3x from each of the terms.
Yeah, and like they would never have done any factoring, but maybe they're in Algebra 1 and maybe they've done some distributing. So how would you, is there a way you could describe that using the word distribute maybe? Like, what are you doing when you're factoring there? Yeah, you're reverse distributing or undistributing, right? When we factor out a 3x, we're literally undistributing that 3x. So what's that going to give us?
X squared.
Okay, you're right. How'd you get that? Okay, and so what's your mental process for that, though? Okay, you divided, right? Now, maybe you just played the game, because you can do this too. You could just say, okay, well, 3x times what is 6x cubed? That's kind of a convenient way to do it, honestly. But even that is still division, right? So when you factor out a 3x and you want to know what's left behind, what's the leftover factor going to be? You always have to divide each term by the GCF to find out, right? 6x cubed over 3x, well, 6 over 3 is 2. X cubed over x is x squared, right? Let's see, negative 9 over 3 is negative 3. X squared over x is x. 12 over 3 is 4, and x over x cancels. You see my point? Okay. When this gets more complicated, as it eventually will, this process is always going to work. When you factor out a GCF, you can just divide that away from each term to see what goes in the grouping symbols, the parentheses. Okay. How about this one? What's the GCF? What's the number part of the GCF?
7.
7. Okay. What's the x part?
XY.
X, and then just a y. Good. Okay. All right. So then what's going to go here?
2x squared.
Yeah. 14 over 7 is 2. X cubed over x is x squared, and the y's cancel, right? What's going to go here?
X.
There you go. Because the 7's cancel, the y's cancel, I'm just left with an x. What goes here?
Negative 1.
Okay, not 0, right? When we cancel vertically, it's a 1. Okay, give me thumbs. All good? Okay. Before we jump into this, how many terms are represented in that expression?
3.
No. 2. How come? Everybody see that? There's just 2 things that are being subtracted there. Each of those things is complicated, right? There are 2 terms. The first term has how many, and so what is a term, by the way? Let's remind ourselves. When we talk about a term in math, those are things that are what? Added or subtracted. Perfect. Okay, the first term has how many factors?
1.
No.
2.
2. How come? Because what are factors?
Oh, the numbers.
The factors are things that are being multiplied. And how many things are being multiplied? Well, I've got that thing times that thing, right? Everybody agree? Two factors there. Now, inside that second factor, there happen to be two terms, but that's very deep inside the function. When I asked you that first question, how many terms are there? We're looking from the outside in, right? From the outside looking into this thing, I only see one minus sign that's connecting a bunch of more complicated things. So there are two big terms in this. Everybody get what I'm saying? Okay? That's important. I think sometimes people maybe haven't thought about organizing expressions in that way, right? How many factors are in the second term? So two, yeah. One there and one there. Okay, so then I've got these two terms. What's the greatest common factor of those two terms? Well, no. What's the biggest thing that divides evenly into both of those? In other words, what's the biggest thing that I could divide the first and the second term by and have it cancel? Say it again. X plus 2. Yeah, right? Everybody get that? Of those two, I've got two factors in the first. I've got two factors in the second. And the common factor is the X plus 2. That's the only one that's the same. Okay. So my GCF is X plus 2. So what does that mean we're left with for my first term in my answer then? 6, right? Because if I divide the first term by X plus 2, I'm going to get, those are going to cancel, right? And I'm just going to get 6. Okay, what goes there? Y, absolutely. Again, I cancel the X plus 2's and I'm just left with a minus Y. Okay, give me thumbs. Okay. Okay, so what about one like this? The point here is that when we start with a negative leading term like this, a negative leading coefficient, this is not like it's some hard and fast rule in math, but this is generally a very good idea. When you factor out the GCF, take the negative sign with the GCF, right? It's no big deal to have a negative greatest common factor, but it's a little bit cumbersome if we've got some big polynomial that starts with a negative leading coefficient. That's going to make things tougher for the rest of the year if we don't get in that habit, because eventually we're going to be factoring, like tomorrow, 4-term polynomials. Again, way easier to do if the leading term is positive. We'll go back and factor trinomials, get some review of factoring trinomials. Remember, that's way easier to do also, probably from Algebra 1 you remember this, if the leading term is positive. So let's always take the negative out with the GCF. Okay, so then what is my GCF going to be here? Yeah, negative 4a squared, which leaves us with what?
2a squared minus 4a
Plus 1.
Yeah.
Yeah, good. Okay, good. Eventually, we may be able to do something with that. Like if we're, and where it's maybe even more important is when we're solving polynomial equations. Eventually, we're going to be doing things like we're going to be solving the equation, this whole thing is equal to 0. And when we apply the zero product property and solve for the zeros of the red factor, it is way easier when we start doing things like using the quadratic formula to have a positive leading coefficient, right? That definitely makes a big difference. So this is sort of a good thing to just keep in mind. When possible, factor out the negative with the GCF. I don't think you guys need to do that. You're good. I think you're pretty good with this. This is overkill for you guys. Yeah, I'm done for today. You can jump in and work. I'll add a short assignment on factor or greatest common factors.